First of all, I'd like to thank Professor Sohan and Dr. Abhishek for inviting me and giving this stage for competition. I still remember 1 year back, Professor Sohan contacted that let us organize this Indo-French seminar, and I think immediately we responded that yes, in India we should have this activity. So basically, I did my PhD from IIT Bombay, and it was in the discrete time sliding mode control. So I thought, let me solve this problem using the discrete time sliding mode control strategy. And there are very few people in India as well as in the world that they are working on discrete sliding mode control. And I had a very good chat with Professor Roorkee even during my visit at Istanbul in 2014, 15 around. And he initially, thought that, you work in discrete time sliding mode control, but I believe that it is not a sliding mode. The reason we know that yesterday also there was deliberations by Professor Bandyopadhyay as well as Professor Soha that in a discrete sliding mode control usually we don't remain on the surface, but instead we remain around the surface at each sampling instant, and by means of this zigzag motion we reach to the origin, and around origin we oscillate, and that's what we call the chattering, in this discrete sliding mode. So usually we call, this is a quasi-sliding mode control instead of ideal sliding mode. And this was the first presentation by Roorkee that although we are not on the sliding mode control, the discrete sliding mode control can also solve the similar problems, although uncertainty cannot be resolved completely. But if you try to remain as near to the sliding surface, then your robustness property will increase. And then Professor Bartoszewicz came a very well-known paper in 1995 that, at each sampling instant, you be on the surface, and during intersample, you can deviate based on your uncertainty and disturbance. But you have to ensure that at each sampling instant, you are on the surface, and that ensures the robustness. But still, this deviation, makes a challenge, intersample deviation. And these intersample deviation, besides the quality of robustness. So initially when Professor, the Gao as well as Professor Bartoszewicz, when they gave this idea, their reaching law with their control law, the deviation from the surface was of the order of T1 or tau. And they said, okay, this much we can guarantee. We ensure that robustness will be there. But later on, there were a lot of paper came actually, which ensured that this deviation, that is the band around the sliding surface, can be reduced to order of T square. And then recently one paper has come, which is in 2017-18 around, which ensures the band of the order of the cube. So you are reducing your band as close as to the sliding surface. And in this work, we are also trying to do that. So, as far as my presentation is concerned, what I will discuss in this 1 hour, that number one, what is multi-agent system? Because in this gathering, I don't know how many of you know about the multi-agent system, because it's a concept which is derived from computer science. And there is a term we call consensus. So we'll discuss about that. Then a new sliding mode protocol which we have defined, that is, we call it topological discrete time sliding. So it's a new terminology. In the literature, you will not find this terminology, and we did it the first time in 2018, that this term we brought into the literature, that is topological discrete time sliding. So we'll see what is that. And based on this definition, we have, derived certain algorithms which are existing, but we modified it for the topology. That is your Gauss reaching law. Then we have gone into the power rate reaching law. We have gone into the higher order sliding mode control law. We have designed the higher order sliding mode control with this discrete super twisting algorithm. That also we modified. And lastly, you can see we have also tried with event triggered sliding mode. And that also we modified and we made it for multi-agent system. We call it topological sliding mode. So I'll discuss about this protocol design, and we will see that some simulation as well as some experimental designs. So what is multi-agent system? The multi-agent system is derived from, the nature itself, that we can see the board floating, piece pulling. There are several such, examples available in the literature, that even the nature, you can see that, there are multiple systems which are working together and try to solve certain problems, So, one of the challenging problem I was discussing with Dr. Soham also, that, can we replace this bird with autonomous vehicle? Can we replace these birds with missile, so that we can guide together? We can have a formation of these missiles. We can have a formation of quadcopters, and we can solve the problem, real world problem, certain. Maybe civilian, maybe military. So what is multi-agent system? So a multi-agent system, usually we refer it as a system of systems. So we are not working for controlling a system. We are trying to control the system of systems, where multiple systems are there, and we call it agent. Okay, and which makes the multi-agent system. So formally it is defined as a multi-agent system is a set of homogeneous or heterogeneous autonomous agents. So I have used two words, homogeneous and heterogeneous. What I mean, homogeneous system is having the identical dynamics, while heterogeneous system or agents are having different dynamics. So you can say that, one is your quadcopter, another is your hexacopter. So they are heterogeneous. They don't have identical dynamics. So we talk about homogeneous system as well as heterogeneous system. A multi-agent system is a combination of multiple interacting intelligent agents. I have a meaning of this intelligent agent. What does it mean? That intelligence means it can get the information from the neighboring agents and it can send the information to the neighboring. That's what I mean in this context. So further, if I define, then agents are computer operated entities that can sense and act in accordance with the task or objective. So it is based on the what kind of task together they are going to perform, and accordingly they will interact with each other. Now this interaction is very, very important. Now in literature, if you will see that, we have a lot of such cooperative control algorithms available. We call it distributed cooperative control of multi-agent system. It has got very wide range of applications. As I said, you can have an autonomous system, guided vehicles. You can have smart grid. In fact, we ourselves have solved a problem of microgrid where, you have a different sources like wind, solar, fuel cell. Each one can act as an agent. They can share the information with each other, and they can, try to supply the power as per the demand. So agent themselves will discuss, how much power I have, how much power you have. Wind, solar, classical power, battery power, fuel cell. And they jointly decide together that, who will supply how much power. So that's why I put the word that is smart grid. But we have solved for microgrid. Some papers are available on that. We have a haptic collaboration over internet. Of course, unmanned aerial vehicle, robotics scheme, biological system, and many more unexplored area of applications. And recently, we have also developed protocols, sliding mode protocols for formation of quadcopters. I'll not discuss about that here. So what is the main idea in this cooperative control of multi-agent system? Is to design distributed controllers on each agent by using the local neighboring information to reach on a specific global goal. Means not an individual goal, but it's a global goal. So that is what we are also trying to solve here. So under the idea of this cooperation, the agents in multi-agent systems share the information with their neighbors locally and try to reach an agreement to a certain degree. To achieve these objectives, various cooperative algorithms are available, like consensus, then gossip. I think for control engineers, these words are new, I think. But this kind of terminology is used in computer science. You have a consensus algorithm, you have a gossip algorithm, you have a formation algorithm, cloaking, rendezvous, etc., etc. Can be designed. The control algorithm for this individual, task, like consensus, or let us have a gossip among the system, They may agree, they may disagree, So, we are thinking in that perspective, how this cooperative control action can be designed, so that we get this thing, So what is consensus, because I have focused myself on number one, that is consensus. So the consensus means you have to agree with all other agents. In a layman language, if I talk, you have to agree with each other, and you are at consensus. Okay, this is my position. This is your position. Let us maintain. So there are two types of consensus basically. One is leaderless consensus, and another is a leader following consensus. So in this video, what we have seen is a leader following consensus. There is one leader, and then all other birds will synchronize. But there are certain, group of entities who don't have any leader. You might have seen the flock of ships or goat, where they don't have any leader. They move in a group without any leader. So there are two types of consensus basically, as I said. That is, number one is a leaderless consensus, another is a leader following consensus. Now out of these two, we have focused on leader following consensus. There is a reason. There is a reason, because you want to guide something, and in a control engineering or control perspective, we need to do certain tasks. So if you assign the task to leaders, then all other followers will do that. For an example, we recently worked on an algorithm where missiles can be synchronized in time as well as in the space. So, if you have a leader missile, then all follower missiles can adjust themselves, in time as well as in space. Okay, and then they can attack. So if you have a leader, then you can assign certain tasks to this group of missiles or group of robots or group of vehicles. So that is the reason we have focused on consensus of, a leader following consensus, I would say. So those who are in this study, they might have, seen some literature also. But if you see the literature, the consensus study itself is divided in a lot of areas. We will see that, based on the system dynamics, there is a linear and non-linear dynamics. There is a first order dynamics, second order dynamics, fractional order dynamics. You have a high order system, you have a stochastic system, you have a homogeneous system, you have heterogeneous system. So based on this dynamics itself, you have number of systems. Then you have certain theories are there. which can solve this problem. So that is algebraic theory. Then you have a graph theory, matrix theory. Out of this, we have used the graph theory, and that is the word which we have brought, that is topological. Similarly, if you see the time domain, we may have the continuous time system, we may have a discrete time system, we may have sample data system. Communication, we may have a directed, undirected. Graph topology, we may have a fixed graph, we may have switching graph. And we try to solve this problem actually. That system is a linearized system. My time domain is a discrete time domain. My communication is an undirected communication. And my graph, I have used both fixed as well as switching. So if you have seen the birds, after some time, certain birds are plugging in and certain birds are plugging out. So accordingly your graph changes. So, it's a switching graph. We don't have a fixed graph. So we have also tried with that kind of topology. Now type of consensus I have already discussed, that we may have leaderless, leader following. Then other words are also there, other domain like collision avoidance consensus. In autonomous vehicle, we use this term. Bipartite consensus. Certain agents don't want to participate. They disagree, just disagree. I don't want to be fall in line what leader has said. I'll be alone. So something like bipartite consensus. You have a fixed time consensus. You have a finite time consensus. You have a fault tolerant consensus. Now, as I said, fault tolerant consensus, it can take care of the fault also in the multi-agent system. And while working at microgrid, we have tried to solve that problem also. To make a topological fault tolerant sliding motor in a microgrid. So certain fault can occur and you can observe those faults and you can take care of it. And you can make your system stable. The control approaches, you can have an event triggered, LQR, sliding mode, fuzzy, PID, state feedback, H infinity, Lyapunov, LMI. People have used all kind of control algorithms for such, objectives. But we observed that, most of these algorithms are in continuous. Nobody was talking about discrete time. However, all implementation usually is done in a discrete time, because in a multi-agent system, you have to communicate with the agent to leader, agent-agent communication. Now, this communication, if we have a digital communication, then we need a digital or discrete time strategy. And that motivated us for designing all this algorithm in discrete time sliding mode control. That's the motivation. So with this background, I'll start with my first, initial results, what we achieved, And before that, would like to tell you, because I don't know how many of you in this gathering know about the graph theory, but we'll have just one slide on that. So, what is graph theory? So, we all have studied in, I think, our bachelor's or even before that, what is graph? So, graph is having, you have vertices, you have edges, and you have a connection. Okay. And this graph theory we are using for the communication. Okay. So here you can see that 1, 2, 3, 4. For us, it's agent, and in control engineering, we call it system. But it's intelligence. So based on this graph, we can define 3 basic important matrices. D, that is your degree matrix. And you can see the diagonal matrix. So that is based on how it is connecting the other agents. So you can see the number 1 is having only communication with 2 number agent. And you can see 2 number agent is having 2 communication with 1 and 3. So it's a diagonal matrix. Then you have an adjacency matrix with which node it is connected. So based on that, you have an adjacency matrix. And the last one is a Laplacian matrix. That is nothing but the difference between these two. P minus P. Now this we are using for designing our topological sliding mode control. So let us have our first contribution that, we started with discrete time sliding mode protocol for leader following discrete time multi-agent system. So what we did, we started with a homogeneous system, because if we start with heterogeneous system, we'll be in trouble. It will be more complex kind of thing, So we started with a very small problem. Let us take identical systems and let us define multi-agent system with the graph theory, and let us design a simple switching type of sliding mode control in discrete time domain using the Gauss law. So those who are in discrete time domain, the first very interesting law, Ritching law, which was given by Professor Gauss in 1992, 93, and it was a switching type of Ritching law. Okay, so we have taken some graphs, and what we did, we started with a simple system where we have given some disturbance, and I, that subscript I, is representing the agent. No, so system 1, system 2, system 3, and we gave the leader also dynamics, and we derived, based on this graph theory, the entire multi-agent system, okay, which is discretized. So you can see in a discrete domain, In, xk, In to f, uk plus, where xk is nothing but x1, x2, xn. These are state vectors of individual system. Okay, so you have, suppose, n number of agents, then small n cross capital N number of state variables you will have. Okay, so let's say my identical system is second order and I have 4 agents. So I'll have 2 into 4, 8 state variables. So back. Accordingly, my control input will be there, U1, U2, U3, Un. So n number, capital N number of agents are there, and these controller will be deployed on each agent, and that is why it is called distributed discrete time. So you need not to put in a centralized, because all, like a bird, all agents are distributed. You have to deploy your control algorithm on each agent. This is how we started with the system. Then we define the, consensus error. This is also well known. And from this consensus error, here it is, this is the error. This is AIO is called pinning gain. And that is the difference between the leader and the first agent who are in connection. While this error, xi minus xj, that represents the state information between ith agent and jth agent. So you can see only the neighbor agent of the leader will have the information of leader, not the last one. So based on this, we define the consensus error, and based on this consensus error, we design the first sliding surface, because in sliding mode control, 2 things you have to do. Number 1, you have to design a sliding surface, and second one is the nonlinear control. So based on this, we designed the topological sliding surface, and that comes out to be this 11 number, you see. And further, for analysis, we are extending it at k plus 1 instant, and to do further, we defined this S tilde k plus 1 in this form. So this is my multi-agent system actually, where this S is the surface of all agents in a topological form. So based on this, we have written the Gauss-Ritching law. This is for individual system, and this is for your global system, which is system of systems. And here you can see that tau will be the sampling time, tau 1, tau 2, tau 3, it may be different, but since we have considered homogeneous system, our tau will be same, the sampling time. And that is what the initial consideration even. And these are its, the gain. Since homogeneous systems, our gains will also keep the same initially. And based on that, we designed the first control law. We call it topological discrete sliding mode protocol. Simply. using the graph theory. And in literature, we are the first who have, presented this kind of control law, which is using the graph theory. This is the first. So we tried to simulate this, of course, because this is a very basic result, we just started our research. So we took a very simple system. I'll not go into more details of, all mathematical analysis. The reason, we have to see that, what is the necessary for convergence. So we derived it that all the, your eigenvalues should lie in the circle. So we have gone into that analysis also. We have taken the dynamics of xk plus 1 using the control law, and we derived the condition, okay, that how all the eigenvalues of multi-agent system should lie in a inner circle, inside a unit circle. So I'll not go into those details, but we proved it, these certain conditions are there, is available in the literature. At the same time, we have to also prove the stability. So in this multi-agent system, we have to prove the global stability, not of local individual agent stability. And we use the Lyapunov concept for this also. And we come out with this theorem that if this is the condition, if this is satisfied, this is surface of global system, then, your G should be positive. This G should be always positive. Then only your system will remain stable. That will be a global system. And there is a proof also. I'll not go into that. So we took a small simulation. We have taken the second order system. And you can see we have taken one leader and this follower. Agent 1, agent 2, agent 3. This is our communication topology. Okay. And we applied the control law, which we derived. But before that, we have to define the D matrix, A matrix, and Laplacian matrix, which we derived from the communication graph itself. And this is the sliding gain, which we have considered for the system, and we have given some distance so that we can check the robustness. So here you can see the blue one is the leader and others are followers. Okay, we have taken some initial condition for each agent. Even for leader also we have taken some condition, and leader dynamics is there. And you can see asymptotically all followers are following the leader. So we can say it's in consensus. And this is about velocity, because we have two state variables, position and velocity. So this is about velocity. So in velocity you can see there is some chattering, but it is synchronized with the leader. And this is about the control law on the ith agent. So on each agent, whatever we have deployed the controller, that U1, U2 and U3, you can see there is a switching as per the Gauss switching law, and there is a sliding surface also. So we have 3 sliding surface because we have 3 followers. So you can see there is a band also because we have used the Gauss switching law. So there will be always a band. And that's what initially I told you. In a discrete sliding mode control, we don't remain on the surface. Instead, we have a zigzag motion, right? So this is sliding surface, and actually we are getting the same results what we have expected from the mathematical derivation. Okay, I'll not go into more detail of this, but it is synchronizing. So these are some results actually. Okay. So initially we conclude, that okay, we have designed some novel topological discrete sliding mode control, and we analyzed for its stability and this thing. But there were questions were there, how much time this will take for consensus, because you have hardly 3 followers right now. But suppose you have multiple followers, and each one has to be in a consensus with the leader. Each one has to synchronize. So leader will, the follower 1 will synchronize with the leader. Once it is synchronized, follower 2 will do, follower 3 will do, follower 4 do. And based on your communication topology, each one brings themselves into a consensus. So how much time it will take? See, in a system control, we know that, how much time it will take for stability, for reaching to desired position. But for a consensus, how much it will time? So that derivation was still pending, and that motivated us to work further. And that's our next part. Analysis for a fixed time, steps required for consensus of leader following the events. So in this analysis, actually, we tried to find out, how much time it will take to bring all the systems into a consensus together. And entire multi-agent system will be in a consensus. So this is what the theorem we have brought, that, the maximum time this will be required, where AI star is given by this. So it's a complete mathematical, 2-page derivation. I'll try to skip it over here. But let me tell you, this is exactly what we get in our simulation, what we derive. And this is available in the research paper also, you can refer. So this is the ultimate time, maximum time all, agents will try to synchronize. So what we did, that, that was the earlier one work with the Gauss reaching law. So we thought, let us see the other reaching law also works or not. Because the Gauss reaching law is it has a very big band, and we are compromising the robustness. So with my student, we were sitting, let us try with the power rate reaching law, because power rate reaching law will provide you, less band and fast convergence compared to Gauss reaching. Okay, so we derived in a similar way with the same sliding surface, same approach, but we used this time the power rate reaching law, and we derived this control law, and we also derived how much time it will take for synchronize for function. So this we derived, and then instead of taking a simulation result, we have used a existing helicopter system in my laboratory. Okay, and then of course model is there, and we have used the linearized system only. So we have used this discretized model EI and FI, and since I am telling you that we have used the homogeneous system, so we have taken the same kind of graph, but now instead of numerical example, now we have a system. So we have a one helicopter, second one leader, and 3 are followers. And in this helicopter system, we have to control both the pitch angle as well as yaw angle. Okay. And we were trying to see how they act. All 4. So same approach we did, simulation, and D matrix, A matrix, diagonal matrix, adjacency matrix, Laplacian matrix. We applied, we found out sliding gain also. And let me tell you this, finding this sliding gain is not easy, because here you don't have one system. If you have a one system, you can use pole placement or any cost function, and you can derive using L2R approach. You have sliding gain. But now you don't have one system. You have a system of systems. So you have multiple gains actually. Okay, so this is also a challenging problem to design this sliding gains. I'll come to that. So we have given some disturbance. Here you can see that each position is also nicely synchronized of all helicopters. So you can see actually all helicopters move like this, together. One will go, leader will go like this. So all other helicopters will also go like this. You will move your helicopter in this dimension. All helicopters will move in this direction. So very beautiful results we had. Sorry, I could not bring which we have applied actually on the system later on. So I'll skip. I'll be quicker. So many results are there, and very important, the number of steps. So you can see 134 steps are required if I am using the Gauss reaching law for position. For velocity 173, and power rate reaching law, you can see it has reduced. Not only that, the order of scattering magnitude, which has gone down from order of tau to order of tau square. So band has also reduced. You are on the surface itself. So these are few more results about agents. I have to go fast. Okay. So position consensus and velocity consensus, and we did some. Okay. Now problem was, with the switching graph topology. No, because right now we have used the fixed graph where agents are fixed. Now we can switch the graph. Like agent is coming in and agent is going out. So your graph topology will change. Okay. So what we did in this case that, we designed similarly the surface and other things. But the point is that your graph is changing. So we have taken 3 types of topology. You see, you have 6 agents, including agent. And in the first topology, you can see 0, 1, 2, 3 are in consensus. In the second topology, you have 0, 5, 4, 3 are in consensus. And in the third topology, you have a, 5 is also out of the graph. Like a bird, in the initial video, bird can enter, but can go out. Now, these graphs are to be defined, G1, G2, G3. And based on that, we have to define the Laplacian matrix, adjacency matrix, and like that. And thinning gain, sliding gain also. And we have got this. But only thing is that, we have now 3 graphs, G1, G2, G3, and graphs we have changed after 50 number of steps. So after some time, from G1, the graph G2 will come into the picture. After 50 steps, G3 will come in. So agent will change. And how many number of steps will be required for the consensus, that also we calculate using this. So I'll be little bit quicker on this. And you can see that with Gauss and power rate reaching law, we have developed this. So very beautiful results we are getting. Now point is that, with both Gauss reaching law as well as with the power rate reaching law was the chattering. And still when there is a chattering, so your agent will try to chatter. This is a leader, let us say, leader bird. Then once it is consensus, even after getting into consensus, there will be chattering. And this chattering will go on and on, with all the systems. So we want to reduce this chattering. And that's why we have gone into a higher order sliding mode control. So I'll not, due to this time constraint, I'll not be able to discuss more on that. But this is how we have designed the control law using the same concept of designing the higher order sliding mode. Dr. Soham has also designed a very nice higher order sliding mode control. And in fact, we have used relative degree too, but we call it higher order. So that also we have taken for this consensus. This will be the band. I think what you have derived, same we have derived for the system of systems. We have derived for system. We have developed for system of systems. So this will be the ultimate band. I think it is similar to what you have derived in your paper. We have used the super twisting algorithm for this, and topological control law is designed. And I want to show you, the other problem which we have solved, that we have taken the robotic arms and we are trying to synchronize them. And this, how much time? So what we have done, this is the laboratory setup, experimental, where we have a robotic joint. We have 2 arms, 1 arm and second arm. So, we try to synchronize this first arm and then second arm also. And there is a lot of coupling effect and other things. And that is why the sliding mode control is important, because it takes care of, all kind of uncertainties. You will see very smooth results we are getting. I am going to show you one of the results. So we have, developed the algorithm for this kind of system. You can see all systems are homogeneous, but in the next phase we have taken heterogeneous arms. All arms can synchronize. They can communicate with each other. Even we tried with changing the graph. It is not like that this is the way of graph, that leader is communicating with follower 1, 2 and 1 with 3, or like that. We change the graph also. Then we also check the result. Almost same results we are getting. A very important thing is that, in our laboratory setup, we had only one setup, but we need multiple setup. So what we did that on different processor, we put this ARM model. So we had one leader, which was also virtual, and all other followers. Out of that, only one follower was the actual one. Rest all were virtual, and we tried to simulate this one. And nicely they were communicating. So I'll show you some results. You see how this robotic arm is moving, and all followers are also following. These results are there, and these are published. We have discussed about the performance also, how good performance we are getting with higher order sliding mode control with relative degree, super twisting algorithm, and we have few more, stage 1, stage 2. So we have derived performance also, and nicely the last one, event triggered, I'll skip it. I think event triggered is already discussed, but this also we have implemented on the robotic arm, and this is the event triggered functions we have defined, and Dr. Abhishek is there to comment on this work. So this is the control law, and the same system we have considered, and the same followers are there. You can see the consensus are there, control law, control inputs are there to each agent, and this is what the event triggering instant. So on the left side you have simulation result, on the right side we have a experimental result. So in event triggered protocol, the controller actually act when there is some event occurs. That event is already defined. So these are few results. I'll not be able to. Okay, the last one is about the heterogeneous. So we have two different dynamics. As I said, in a heterogeneous system, we don't have the same identical system. So I'll not go into that, but I'll show you the one video which I have brought. This is about heterogeneous system. You see, two arms are there, and others are virtual. Let me tell you, no chattering, very smooth. This is with the higher order sliding mode control with super twisting algorithm. So all synchronized. Now this is for only testing purpose. We have applied this to lot of guidance. So, coming to the conclusion, F5. Okay, so you can see all the protocols in this. Whatever I have discussed in more detail with all parameters, all derivations will be able to this book, that is discrete sliding mode protocols. But we have also established this thing. As I said, consensus is one of the problems. Another problem which we have handled is a formation. So we have also developed robust sliding mode protocols for formation of quadcopter swarm. So they can make any formation, whatever you want. And yesterday, I think Dr. Kiran also presented some, trajectory tracking and other things. But we have gone into a swarm where they communicate with each other. And graph theory we have used. So we call it topological sliding. So I think due to time constraint, I have wound up quickly. Thank you very much.
Long live India and France friendship.